Let's get into it. Number 8, the baby black hole that ate like a monster. In standard astrophysics, there's a rule, a speed limit. When material falls toward a black hole, the radiation released pushes gas away from the black hole, creating a natural brake. We call this the Eddington limit. It's like a cosmic governor on a truck engine. It prevents the black hole from feeding too fast. For decades, this has been treated as gospel, textbook physics. The maximum meal size for any black hole is determined by this one simple equation. It's comforting, really. Limits, predictability, order. But in November 2024, everything got weird. Astronomers led by Hyewan Suh, that's Hyewonsuh, from the Noir Lab discovered something impossible using the James Webb Space Telescope and the Chandra X-ray Observatory. They found a supermassive black hole at the center of a dwarf galaxy. It existed just 1.5 billion years after the Big Bang. And this thing was eating material at 40 times its Eddington limit, not 1.5 times, not double. 40 times faster than the cosmic speed limit allows. Think about that for a second. The Eddington limit is supposed to be an absolute ceiling, like saying a car can only go 65 miles per hour, then watching one zoom past at 2,600 miles per hour. The math doesn't just break, it shatters. According to the equations that govern how radiation pressure works, this black hole should have been pushing its own food away. It should have starved itself. Instead, it went on a feeding frenzy. The physics gets worse when you consider the implications. If this black hole has been consuming material at this rate for just 100 million years, it wouldn't need to have started as a massive seed. It could have grown from a regular stellar black hole, maybe 1,000 times the sun's mass, and reached its current size in the blink of a cosmic eye. We're talking about growth that should take billions of years compressed into millions. Imagine you're an astronomer watching the data come in. You've spent your career building models, running simulations, making predictions based on the laws you trust, and then you see this. A black hole the size of a small city, feeding like it's got no tomorrow, breaking every rule you thought was sacred. You'd feel your understanding of the universe crack. The worst part is this might not be alone. If one black hole figured out how to cheat the system, how many others are out there doing the same thing right now? How many feeding frenzies are happening in the darkness of the early universe, invisible to us except for the fact they shouldn't exist? We're looking at a cosmos that doesn't follow the instruction manual. Number 7, the impossible brightness at cosmic dawn. For decades, astronomers believed they understood how galaxies worked. They'd form, stars would ignite. Slowly, over billions of years, supermassive black holes would grow at their centers through careful accretion. Black holes come late to the party. They're the finale, not the opener. Then, the James Webb Space Telescope looked back to the earliest galaxies and found 5 quasars existing between 600 and 700 million years after the Big Bang. And here's the terrifying part. They were in the wrong neighborhoods. Lead researcher Anna Christina Eilers from MIT made this discovery in October 2024. Her team expected to find these ancient quasars clustered in dense regions of the early universe, places packed with galaxies that could fuel rapid black hole growth. That's how physics works. You need fuel nearby. You need a cosmic buffet to grow massive. But these 5 quasars? They were sitting in what appears to be empty space. Sparse. Alone. Almost deliberately isolated. The JWST data showed very few neighboring galaxies around them. Certainly not enough material to explain how they became so massive so quickly. One researcher on the team said something that captures the dread perfectly. Contrary to previous belief, we find on average these quasars are not necessarily in those highest density regions of the early universe. Some of them seem to be sitting in the middle of nowhere. This breaks every model we have. The standard theory says dark matter filaments, like gravitational highways, pull gas into dense regions where galaxies can form and feed black holes. These quasars shouldn't exist where they are. They should be invisible, dead, left behind as ancient failures. Instead, they're luminous, massive, present. The facts don't line up, and that means our understanding is incomplete. There's something about black hole growth we don't know, something that allows them to feed in isolation, something that makes a mockery of our models. We're like people who thought we understood how the ocean worked until we found fish thriving in puddles. Number 6, the record-breaking feeding machine. Fast forward to February 2015. Astronomers from Peking University and the University of Arizona announced one of the most disturbing discoveries in modern astronomy. They found a quasar called SDSS-J0100 plus 2802, using the Sloan Digital Sky Survey combined with data from the Y satellite. This quasar existed 900 million years after the Big Bang. Let that sink in. 900 million years. The universe was barely out of infancy, and this thing was already ancient. The black hole at its center weighed 12 billion solar masses. Billion. Our Milky Way's black hole, Sagittarius A star, weighs only 4 million solar masses. This black hole was 3,000 times heavier. 3,000 times larger than the one at the center of our entire galaxy, and it was shining with the brightness of 420 trillion suns. Let that number settle into your brain for a moment. 420 trillion. If you stood on the surface of this quasar, and you couldn't because you'd be incinerated instantly, the light would be so intense you wouldn't just be blinded, you wouldn't exist anymore. The radiation would disintegrate every atom in your body. The lead author, Xu-Bing Wu, that's Xue-Bing Wu from Peking University, called it a giant in the young universe. He was being polite. It was an abomination, a thing that shouldn't exist. Cosmology didn't have an explanation for how a black hole that massive could possibly form in just 900 million years. Think about the growth rate. At the Eddington limit, the supposed cosmic maximum, it would take billions of years to accumulate that much mass. Yet here it was, impossible and real, captured in observational data, peer-reviewed, published in Nature, undeniable. What that black hole tells us is that something in the early universe was accelerating black hole growth in ways our theories don't predict. There was a frenzy, a feeding spree, a violation of everything we thought we understood about how objects grow in space. Number 5, the emptiness problem gets worse. Jump forward to January 2024. Researchers led by Roberto Maialino from the University of Cambridge used the James Webb Space Telescope to study an ancient galaxy called GNZ 11. This galaxy existed 400 million years after the Big Bang. 400 million. That's not just early. That's terrifyingly early. We're talking about a time when the universe was a baby, when the first stars were just beginning to form. And yet, here was a galaxy with a supermassive black hole at its center. The black hole itself weighed about 1.6 to 2 million times the mass of our sun. Relatively small compared to later black holes, but still, in an infant universe, this is a monster. And the kicker? This black hole was feeding at a rate 5 times faster than the Eddington limit. This shouldn't be possible. The physics is absolute. Yet, Maialino's team saw the evidence clearly. They detected the telltale ultraviolet glow of hot gas spiraling into the black hole's accretion disk. The black hole was consuming material far too rapidly for its own good. It was like watching someone eat so fast they're destroying their own digestive system, but they can't stop. What made this discovery even more ominous was what they found next. The black hole wasn't just growing. It was expelling gas from the galaxy in ultra-fast winds. The very act of consuming matter so voraciously was pushing material away. It was poisoning its own food supply. This black hole was literally killing the galaxy that spawned it, cutting off the formation of new stars, while also cutting off its own source of fuel. Imagine being the architect of your own destruction, growing so fast, so hungrily, that you choke yourself off from the resources you need to survive. The universe is full of black holes that might be doing exactly this right now, feeding so hard they're committing suicide in slow motion. The bigger question haunts every astronomer studying this era. How did a black hole become so massive so quickly in such an empty cosmos? What mechanism allowed this? The answers we have don't fit. Number 4, the impossible quasar from deep space. In November 2023, an international team led by Andy Goulding from Princeton University made a discovery using both the James Webb Space Telescope and the Chandra X-ray Observatory. They found R1. That's UHZ-1. This galaxy existed only 450 million years after the Big Bang. The supermassive black hole at its center weighed somewhere between 10 to 100 million solar masses. It was located 13.2 billion light-years away, which meant the light we were seeing had traveled through the entire age of the universe to reach us. What made OZ1 special wasn't just that it was ancient. Every black hole we're discovering at this era is ancient. The problem is that OZ1 shouldn't exist at all. The black hole inside it is too massive for the time available. According to everything we know about how these objects grow, it needed billions of years. Instead, it had only 450 million. Goulding noted that they needed both Webb and Chandra to find it. Webb could see the distant galaxy. Chandra could see the X-rays blasting out from the feeding black hole. Only by combining two of the most powerful telescopes ever built could they confirm it was real. That's how subtle and strange this thing is. It hides in the infrared glow. You need specialized instruments just to prove it exists. But once you have that proof, it stands as testimony to a process we don't understand. The discovery of UHZ-1 forced astronomers to confront a hard truth. The early universe was making black holes faster than we thought possible. The mechanisms were different. The growth rates were insane. We were building our models on foundations that didn't match reality. Number 3, the chaotic acceleration nobody predicted. Skip forward to January 2026. Researchers at Maynooth University in Ireland published a study in Nature Astronomy that might finally explain what's happening. And the explanation is almost as unsettling as the mystery. A PhD candidate named Daxal Mehta, that's Daxal Mehta, and his advisor Dr. John Regan ran sophisticated simulations of the early universe. They wanted to understand how small black holes, the kind you'd expect to find in the early cosmos, could grow into the supermassive monsters we're actually observing. What they found was that chaotic conditions in the early universe created perfect conditions for extreme black hole growth. The early galaxies weren't orderly. They weren't neat and structured like the Milky Way. They were violent, chaotic, turbulent. Gas clouds collided. Stars formed and died in rapid succession. The universe was basically a demolition derby. In these chaotic environments, small black holes experienced what they call super Eddington accretion. They went on feeding frenzies. Their accretion disks became unstable. Material piled in faster than the radiation could push it away. The chaos overwhelmed the physics that normally regulates black hole growth. Think of it like a dam in a flood. Normally, the dam controls the flow of water. But if the flood is massive enough, chaotic enough, the water overwhelms the structure. The dam becomes irrelevant. Water flows everywhere. That's what was happening in the early universe. The chaotic influx of material was so extreme that the Eddington limit became more like a suggestion than a law. Black holes that should have taken millions of years to grow by a certain amount did it in thousands of years. The simulations showed that these tiny baby black holes, maybe 1,000 times the sun's mass, could grow to millions and billions of solar masses in just the first billion years of the universe's existence. Not through mergers, not through special mechanisms, just through raw, chaotic, violent feeding. This discovery should have been comforting. Finally, an explanation. Finally, physics that works. But there's a dark edge to it. If the early universe was that violent, that chaotic, that unpredictable, what does that tell us about the stability of the structures we see today? What forces shaped the cosmos when it was so young and wild? Number 2, the impossible brightness across all wavelengths. Jump to January 2026. Researchers from Seida University, that's Waseda, and Tohoku University in Japan, made an announcement that shattered what remained of our understanding. Using the Subaru telescope, they identified a quasar that had been devouring matter at 13 times the Eddington limit. 13 times. Not 5 times. Not double. 13. This quasar, nicknamed ID 830, existed about 12 billion years ago, when the universe was roughly 1.8 billion years old. It weighed about 440 million solar masses, and it was doing something that current models say should be impossible. It was bright in X-rays while simultaneously launching a powerful radio jet. Let me explain why this is a problem. When black holes grow at super Eddington rates, the accretion disk becomes chaotic. The radiation environment becomes unstable. The standard theory predicts that X-ray emissions should be suppressed. The jets should weaken or disappear. The system should be a wreck. But ID 830 was doing both simultaneously. It was feeding at 13 times the speed limit while maintaining brilliant X-ray output and powerful radio jets. It was like a car going 1,690 miles per hour while simultaneously traveling in a straight line and turning sharp corners. The lead researcher, Sakiko Obuchi, that's Sakiko Obuchi from Waseda University, said the discovery may bring us closer to understanding how supermassive black holes formed so quickly in the early universe. Translation, we have no idea how this works. The quasar is likely caught in a brief transition, a moment when an enormous amount of material is being pulled in all at once, violating the Eddington limit completely. But this moment shouldn't exist. These transitions should be rare, invisible, fleeting. Yet here it is, caught, observable, defying our models. Number 1. The universe-spanning survey that changed everything. Zoom back to June 2024. Researchers from Penn State University, led by graduate student Fan Zhou, that's Fan Zhou, and Professor W. Neil Brandt, released a comprehensive study that fundamentally altered how we think about black hole growth. They combined data from NASA's Chandra X-ray Observatory, the European Space Agency's XMM Newton, and the Max Planck Institute's Rosetta telescope. They studied 1.3 million galaxies. Within those galaxies, they identified and characterized over 8,000 actively growing black holes. This was the largest, most detailed study of black hole growth ever conducted. They tracked how black holes grew over 12 billion years of cosmic history, from when the universe was just 1.8 billion years old to today 13.8 billion years old. What they found was systematic, consistent, undeniable. More massive galaxies grew their black holes faster through accretion, always, at all cosmic epochs. The pattern held everywhere they looked. But here's what's unsettling. The data proved that black hole growth through accretion was far more efficient than we'd thought. Far more rapid, far more violent. The universe wasn't growing black holes on a measured, controlled timeline. It was growing them fast, aggressively, in ways that current models weren't fully capturing. The sample size made it impossible to dismiss. You can't argue with 8,000 rapidly growing black holes across 1.3 million galaxies. You can't say it's an anomaly. It's the norm. And the norm is that black holes in the early universe grew faster than the textbooks said they could. These researchers essentially proved that the Eddington limit, that cosmic speed limit we've relied on for decades, isn't as absolute as we thought. Black holes can and do exceed it. They do it routinely. In fact, rapid growth through super Eddington accretion might be the default state for black holes in the early cosmos, not the exception. We built a universe in our heads, a universe with rules, with limits, with predictable growth timelines for black holes measured in billions of years. We thought we understood the cosmos because we understood the equations. But the actual universe doesn't care about our equations. What these 8 discoveries show us is that the early cosmos was wilder, more violent, more chaotic than we imagined. Black holes didn't grow on schedule. They didn't follow the textbook. They devoured material at impossible rates, launched powerful jets from turbulent accretion disks, and reached billion solar mass sizes in the blink of a cosmic eye. We are explorers with incomplete maps, confidently pointing out the territories we think we understand, while the actual landscape keeps contradicting us. We name things to feel like we've conquered them. Supermassive black holes. Eddington limits. Super Eddington accretion. But naming something doesn't mean understanding it. The early universe is a living testament to how much we still don't know. If you want to keep diving deeper into the mysteries nobody's supposed to ask about, hit that subscribe button and make sure notifications are on.